All right, so far we have in this topic of higher dimensional physics, we have looked at the idea of compactification and identification, and we have also talked about extra dimensions in somewhat of detail, and then I have discussed the hierarchy problem, which is one of the applications for this topic of higher dimensional physics, where you propose an idea of extra dimensions to understand why gravity appears so weak when it is compared with the other forces of standard model, right? So in this lecture, let's move on to the topic of Kaluza Klein theory, which is a theory that, or it's a framework to study theories in extra dimensions, right, or in higher dimensional spaces. So I'm going to start with briefly with the history of Kaluza Klein theory, and then we'll move on to the mathematics and the framework for this theory, and then I'll talk about the scalar field in 5 dimensionals, right? Right. So Kaluza Klein, which is also short written in shorthand as KK, Kaluza Klein reduction has been, it has always been a very vital ingredient in the attempts to form a relation between D is equal to 4 physics to D is equal to 10, and well, to be honest, even higher dimensional theories. D is equal to 10 is known as super strings, and then you have even higher dimensions where you move on to D is equal to 11, which is used in super gravity. Now, uh, this is now recognized as the low energy effective description of what is called a D is equal to 11 uh, M theory, right? So I'm not going to go into the details of these super strings, super gravity, or M theory. This was just to tell you about why do we need, or where does Kaluza Klein theory helps us, right? Okay, so now in the year 1921, there was a mathematician called Kaluza. He put forward the idea of acquiring a 4 dimensional Einstein Maxwell theory, and he started from the Einstein's equations for gravity in 5 dimensions. Now, the way this works is that you assume a 5 dimensional manifold, let's call it M, and it is the product of a 4 dimensional manifold and a circle, which is S1. Now, this is similar to the diagram that I even drew in one of the previous lectures, where the circle was something like this, and you had your usual 3 space dimensions along this line. Your 5th dimension was along this circle, and your time dimension was along this axis over here. Anyway, moving forward, we have this thing that your 5 dimensional manifold M is a product of these two, where M4 is the 4th dimensional space-time and S1 is your circle. Now the 15 components of the metric, they can be decomposed from a 4 dimensional perspective into 10, which describes the gravity tensor. Now 4 of them forms the components of U1 gauge group or U1 gauge field, while 1 degree of freedom is left representing a scalar field phi. Now, using the method of Fourier expansion then on our fields and retaining only the zero modes, and then you integrate along this circle S1, you arrive at a theory in 4 dimensions that is invariant under both 4 dimensional general coordinate transformations, which I'll be referring to as GCT, and also this U1 gauge group or gauge transformations. Now, everything that I'm saying right now, we'll be discussing it in mathematical detail later on, even in this video and in the other videos as well. But now let me also mention that Kaluza, in his primordial work, he assumed that the zero mode of the scalar field as a constant. So which would just be that the phi zero component was, he took it as a constant, let's just call it 1. But in any event, the value of phi 0 had to be positive, and the reason for that is to ensure the proper relative sign of the Einstein and Maxwell's term, which implies positive energy solutions. And so in turn, this also forces the fifth dimension to be space-like and not time-like. And so this is, in one way, it proves that your extra dimension must be space-like. Now, moving on from this, 7 years later, Klein made use of Kaluza's idea in an attempt to explain the underlying quantum mechanics of Schrödinger equation, which you can write it down from the eigenvalue equation h psi is equal to E psi, and where h is your operator and E is the eigenvalue of your Hamiltonian. Anyway, he what he did was he derived this Schrödinger equation from a 5-dimensional space-time in which the Planck constant is established in connection with the periodicity along this closed 5th dimension. Now, furthermore, he also talks about the size of the compactified circle, which in turn gives the extra dimensions a more physical meaning. And then in 1926, Klein suggested a relativistic generalization of the Schrödinger's equation, and he started from a massless wave equation in 5 dimensions, and he arrived at the 4-dimensional Klein-Gordon equation. So this was just some of the history of the theory of Kaluza and Klein for higher space dimensions. Now let's move on to the framework for the Kaluza Klein theory. So let's go to the next page and let me write, and we are going to talk about the framework of the theory. Now, let's start with the original framework. So in the original framework of Kaluza and Klein, the particles are free to propagate in the extra dimensional compact space along with the 4-dimensional space, which just means that the volume of the new dimensions must be very small when it is compared to the volume of 4-dimensional space. And the reason for that is that any undesirable interaction is not allowed with the present experimental data. So now consider the case of a 4-dimensional Minkowski space and a circle, which is again your M4 cross S1. The wave function of a scalar field can be expanded in Fourier series along S1 as such that you can write down your phi of x mu, where your x mu is just your 4 dimensions, and let's call the extra dimension 5th dimension, let's call it y. This can be written as 1 over by using the Fourier series expansion. You can write it as 1 over 2 pi r summation over n, where n is, it belongs to, well, all the integers, and then you have exponential iota n y over r. Then you have multiplied by phi n of x mu. So you can see that we have expanded the extra dimensional part in Fourier series. And here again, this y coordinate, it lives on the circle S1. And S1 has a radius r. So r is the radius of this circle. And n over here in these equations, let me just make this more clear. Iota n. N in this equation is the usual eigenvalue of the one-dimensional angular momentum operator. And you'll see that this n, this defines the modes, what we call the modes, right, for Kaluza Klein tower. Well, let's not go any further. Before moving on to the scalar field in 5 dimensions, let's discuss on how a higher dimensional field theory may reduce to a 4-dimensional one after the compactification, where the identification is y and y plus 2 pi r. For the compactification of the extra dimensions. Now, for the purpose of illustrations, we'll consider one extra dimension that is compactified on a circle with radius r. As you can see in this diagram, this is a circle whose radius is r. This is the this is y coordinate lives on this circle, and here you have your x. Let's call it x alpha, where alpha is for space time, and this one is your x0. Sorry, alpha is just for your space indices, space coordinates, and this is your time coordinate. Okay, now what I'm going to do is, let me tell you how will I indicate the coordinates. I'm going to use this thing, that xm, where remember m is this thing, it is a product of your 4-dimensional space time and the circle S1. I'm going to write it, these coordinates, as x mu comma y, where x mu is your let me start with m. M is runs from 0, 1 and up to 5, right? And you can see that because x mu or mu runs from 0, 1 to 4, while sorry, not 4, up to 3, right? While this y is simply your x5, so it's the extra coordinate, right, in the higher dimension. So, or you can say that it is the coordinate in the direction of the extra dimension. Now let's go a bit more further and talk about scalar field in 5 dimensions. So I'm going to consider a pretty straightforward example of a free scalar field phi, right? And let's look at its action first of all. It is given as the integral d 5x, because we're talking in 5 dimensions now. 1 by 2 partial mu, well, you'll not have partial mu, you'll have partial m, because we're again talking in 5 dimensions, of phi x mu comma y, and partial m phi x mu comma y. Right. Now note that in 5 dimensions, you can see that the scalar field has a mass dimension of 3/2, right? 3 by 2. Now, due to the compactification of the extra dimension, the field value has to be periodic in y, right? Because of compactification. And therefore, we will have phi of x mu comma y, and our identification was this thing. So you'll have y plus 2 pi r is the same as phi x mu comma y, right? So this just means that if you travel along this circle with a circumference of 2 pi r, you come back to your original position, which is x mu comma y. Now now recall this Fourier decomposition that I wrote, this one, for your field phi. If you take this decomposition of phi along y, let me just write it down again. So it's phi of x mu comma y is equal to 1 over under the root 2 pi r. Then you have summation over n, where n belongs to integers, e I n y over r times phi n of x mu. Now the reality of phi imposes, or it forces the condition that phi of negative n is equal to phi of n dagger, right? And now what I'm going to do is I will insert the Fourier expansion into this action over here, and let's see what do we get. Now comes a bit of lengthy steps, or not lengthy steps, but let me just anyway reduce my pen size so I have more space. You have action is integral d, you can break down this action into 4 and 1, right? So you have d4x, and then the fifth dimension is y, so you have dy, and we have 1 over under the root, we have 1 over 2 pi r, and you have sum over m comma n 1 over 2, where I'm just going to write down this thing now, and I will break it down as well. So you have 1 over 2 partial mu phi m of x, and then you have e iota m over r times y, then you have partial mu phi n times e iota n over r times y, and then you have negative, let me write it down over here, you have minus 1 by 2 iota over r times m phi m of x e iota m over r times y, into iota n over r phi n of x times exponential iota n over r y, and that's pretty much it, right? Okay, so now this thing, all I have done is I have inserted my Fourier series expansion into this action over here, where the Fourier series expansion is this one, right? So let me just write it over here. So this is the Fourier series expansion, and this is your action. Right. So the next step is to simplify this a bit, where I'm going to uh, I'll combine these m and n with the exponentials, right? So you have this thing and you have this thing. So let's just do some simplification, combine these things, and let's see what do we have. It will be integral d for x, and you have sum. Let's combine the sum as well. So m and n of integral dy 1 over 2 pi r. You have e iota. Now you'll have m plus n over r times y, and then you'll have 1 by 2 times partial mu phi m of x times partial mu phi n of x, right? And then to this you have added m times n over r squared now times phi m of x times phi n of x. So we're just combining some of the terms together, and with this then you have, if you simplify this thing, you arrive at integral d for x 1 over 2 sum over n partial mu phi of minus n partial mu phi of n minus n square over r square phi of minus n times phi of n. And this is now your action with the Fourier expansion of your scalar field phi. And now if you look at this equation, and if you separate out the four-dimensional and the fifth-dimensional part, you'll have something like, not exactly, but let me just write it down. You'll have something like 1 by 2 partial mu phi of 0, and you'll have partial mu phi of 0 plus, now you'll have a tower, an infinite series of tower, which is n equals from 1 to infinity, right? So this is an infinite series of particles. These are called the Kaluza Klein tower, right? So it's an infinite series of particles, and it is called a Kaluza Klein tower, which is partial mu phi n dagger partial mu phi of n, right? Now again, let me just say this, that if you look at this from a four-dimensional perspective or a viewpoint, then this action represents an infinite series of particles, which is called the Kaluza Klein tower, right? And this Kaluza Klein tower will have, you can get, if you remember your scalar field equation that you already know from classical field theory. It is partial mu phi partial mu phi minus m squared phi, something like this, right? Or m squared phi squared. And of course you have a factor of 1 by 2 with all of this. But now if you compare this equation with this equation, you immediately see that this Kaluza Klein tower have mass which is of for every nth mode it has mass n over r, right? Now this is simply by comparing these two equations, right? You find out the masses of the Kaluza Klein tower. Now the next thing you can I'll move on to the gauge field in 5-dimensional in next lecture, and then eventually we'll talk about gravity or gravitational field in 5 dimensions later in this series. But now if you take this field phi of x mu comma y, this has a mass or a 5-dimensional mass. Let's call that m0. So this is a 5D mass. Then the 4-dimensional Kaluza Klein particles will have masses which would be mn is equal to, or there will be a square over here. You'll have m0 square plus this thing n over r whole squared, right? So this is the mass of 4-dimensional Kaluza Klein particles if the field phi of x mu and y has 5-dimensional mass, which we called this m0, which appears over here. So you just add this Kaluza Klein tower mass n square over r square to it. And so this is where I will finish this lecture. In the next one, we'll hopefully talk about gauge field in 5 dimensions, and then we'll move further towards talking about gravity in higher dimensions, specifically 5.